Okay, in section 9.2, we go into multi-stage experiments and modeling games. Before you've done this, please make sure that you've read pages 484 through 499 in your textbook. And then you can go on after you've filled out these notes and complete your homework in my math lab. What we're going to do is we're going to talk about tree diagrams first because we're going to be doing multi-stage experiments and those can be helpful in looking at all of the possibilities. So first thing in your notes, drawing one ball from a box is considered a one-stage experiment. But when you go to drawing two balls, that's considered a two-stage experiment. And there's even going to be problems that you come across where it could be a three-stage or beyond that experiment. Tree diagrams are helpful for writing out that sample space, all of the possibilities of the things that could happen in that experiment. It's not mandated that you use a tree diagram. That's completely there to be helpful. So if you do a few and realize that you don't always need those, that's fine too. The multiplication rule is the probability of an outcome along any path of the tree diagram is equal to the product of all the probabilities along the path. And as we do example 1 and 2, I'll show you how that multiplication rule works. As you look at example 1, it says a box contains 4 white, 3 red, and 3 green balls. A ball is drawn at random and not replaced. Then a second ball is drawn. Find the probability that the two balls are the same color. And so this is the first time this semester that we've talked about something not being replaced, and so the box is changed from its original state. On a day like this in a 7th grade classroom, I would come in, say, with a box of candy or a bag of candy. And let's say in that bag I have 12 pieces of candy, and in that bag I have, say, 5 Snickers, 4 Twix, and 3 Starburst. And I go up to the first student and I say, what is the probability that you get a Starburst? Well, they would say 3 out of 12, and then hopefully reduce that. And I say, okay, go ahead and take your Starburst. And when I go to the next student, I say, there's not 12 pieces of candy. How many pieces of candy are left? And they're going to say 11. And I say, okay, well, how many Starbursts are left? And they'll say 2. And so we talk about that their probability of getting a Starburst has changed because one of those Starbursts has been removed and not replaced. And so I say, okay, what's the probability that you get a Starburst? And they're going to say 2 out of 11 now because the first Starburst has been taken out. And I say, okay, go ahead and reach in and get a Starburst. Now, just because I ask them the probability that they get a Starburst doesn't mean they're going to get a Starburst. They might reach in and get a Twix. And so if they get a Twix, that's fine. They might get a Starburst, they might get a Snicker, but the fact is that what is left in the box has changed every time a piece of candy is drawn out. And so we talk about what's left after it was taken out and what the next person's probability is. And so that's a very good way for students to remember what happens when something is taken out and not replaced. That's exactly what's happening right here with the balls. And this type of problem, you could also bring in a box that has the 4 white, 3 red, and 3 green and actually do a little experiment and see what happens every time you take that ball out and you don't replace it. What we're going to do is we're going to draw a tree diagram to help us visualize all of the different possibilities of things that could happen when one ball is drawn and then a second ball is drawn, and then from that we're going to find the probability that the two balls that are drawn are the same color. Okay, so we'll start, and I hope here that I have enough room to do it on this smart board, but we'll start, say, with our first draw. And when I go in for my first draw, I have a possibility of getting a white, or I have the possibility of getting a red, or a green. The probability that I get a white would obviously be 4 out of 10 because there's 4 white out of 10 total balls. The probability that I get red would be 3 out of 10 because there's 3 red out of 10. And green is also 3 out of 10. So if we were just drawing one ball, probability of white 4/10, red 3/10, green 3/10. But I extend this because it's a two-step. I'm reaching in for a second draw. Now in this first one, I'm assuming that I get white first. That's the assumption on this piece of the tree diagram. If I get white first, my second could be white again, or it could be red, or it could be green. So assuming I got white first, if I want to know the probability that I get white second, well, one of those whites has been assumed to be already drawn. So now there's only 3 white and there's only 9 balls. So the probability you get white second is 3/9 here. The probability that you get red, well, you're assuming the first one is white, so there's still 3 red, but now out of only 9 balls. And I know that's kind of hard to see, and I apologize. On the third one, the probability that you get green, assuming we get white first, there's only 3 green left out of 9 balls. Now let's assume that we got red first. So if I get red first, I could get white second, I could get red second, or I could get green second. Now assuming I got red first, all of the white balls are still in there. So I have 4 white, but now only 9 balls left because one has been drawn and not replaced. If I assume that I get red first, getting red second means a red is removed, and considering a ball is removed, I only have 2 red left out of 9. And assuming you get red first, there's still all 3 green left, but now only out of 9 balls. All right, now let's assume we got green first. My second could be a white, or it could be a red, or it could be a green. Now assuming you get green first, on your second draw, all 4 white would be there, but only out of 9 now. For red, you're assuming you got green first, so all 3 red are there, but now out of 9. And assuming you got green first, there would only be 2 green left out of the 9 marbles. So there is a tree diagram, and I apologize, this pen is not very precise, especially when trying to draw things like this. So some of my writing I know is a little bit hard to read. So here's all the possibilities. If I look here, if I follow, I could get white, white, or I could get white then red, or white then green. Or following here, I could get red, white, red, 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 green, etc. The question here is, what's the probability that we get 2 balls that are the same color? Well, that would be the probability that I get white and then white again, or the probability that I get red and then red again, or the probability that I get green and then green again. Well, if you look above on your notes, that multiplication rule says that to find these probability of multi-stage experiments, you follow the probabilities up on the path. So if I look here, white, white, this is white, white, would be 4/10 times 3/9. So that's going to be my 4/10 times my 3/9. We could go ahead and reduce first, or we could go ahead and multiply and then reduce. It doesn't make any difference at all. If you go ahead and multiply, that's going to be 12 out of 90, which obviously is going to be reduced. You could reduce it, or you can reduce it at the end of the problem. That makes no difference. If I want red, 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 red is going to be these 2 probabilities multiplied. So that's going to be 3/10 times 2/9, and this is going to be 6/90, which is also going to need to be reduced. You can reduce now or at the end of the problem. And then we have green, green. Same thing, it's going to be 3/10 times 2/9, which is again 6/90. And so the probability that we get the same color would be the sum of all 3 of these answers, because these are the 3 different situations where you could get the same color. So the probability that we get the same color is equal to 12/90 plus 6/90 plus 6/90. And when we have it left in 90ths, I haven't reduced anything yet, but I also have a common denominator. So when I add all of these up, the probability I get the same color is 24/90, and when I reduce that, that's obviously going to reduce to 4/15 of the time is the probability that I get the same color. So the tree diagram can be very helpful to map out all those possibilities, and then you can follow the path to go ahead and multiply your answers. Now when we look at part B, come down here on part B, it's the same problem, but when we look at this, the ball is replaced this time. So it says a ball is drawn at random, its color is recorded, then it is put back. And so that totally changes the problem. On number 1, part A, the ball is not replaced. On part B, the ball is put back. And so we're going to redo a tree diagram showing what would happen here. So when you go in for that first draw, the probability you got white was 4/10. The probability you got red was 3/10. The probability you got green was also 3/10. Now assuming you drew white first, your second draw could again be a white or a red or a green. When you put the ball back, all 10 balls are still there again. And so the probability you get white is back to 4/10, red would still be 3/10, green would still be 3/10 because the ball is put back, the box is back in its original state. Assuming you get red first, second you could get white, or you could get red again, or you could get green. White would again be 4 out of 10, red 3 out of 10, green 3 out of 10. And assuming you get green first, you could get white second, red second, or green second. And that's again 4/10, 3/10, and 3/10. So it's the same problem, but putting the ball back. Again, I want the probability of the same color. So that's going to be the probability of white, white, or the probability of red, red, or the probability of green, green. And you're going to follow the path on the tree diagram and multiply those possibilities. So white, white would be 4/10 times 4/10, which is 16/100. For red, red, that's going to be 3/10 times 3/10, which is 9/100. And then green, green is 3/10 times 3/10, which is 9/100. And again, if you want to go ahead and reduce at this point, you can, especially, you know, that 16/10 can be reduced. The reason I don't reduce it is because I'm about to add all of those together. 9/100 does not reduce. And so I'm going to go ahead and add all of those together because the common denominator would be 100. The probability that you get the same color this time is the sum of these three answers. So you're going to add 16, 9, and 9. That is 34/100. And now at the end, I'll reduce that answer to 17/50. So the probability I get the same color with replacement, putting the ball back, is 17/50. Where up above, the probability I get the same color without replacement was 4/15. We'll go ahead and go to the next page in your notes. And on number 2, it says, use a tree diagram to list all the outcomes in the sample space when 3 coins are tossed. A tree diagram, again, can help you see all of the possibilities of all of the things that happen. And so we'll go ahead and draw a tree diagram here, and then we will answer these questions. We see in our problems exactly, at least, and at most. We already talked about from the last lesson, this terminology is going to be something that our students typically struggle with. So before we go through, we're going to go ahead and draw a tree diagram, and then we'll use that to write out the sample space. Okay, so for this problem, I'm going to toss 3 coins. So on my first toss, I can get heads or I can get tails. Assuming I get heads first, my second coin, I can get heads or I can get tails. If I get tails first, I could get heads second or I could get tails. Now I still have my third coin, so I stem off again. My third coin, I could get heads, or I could get tails, or I could get heads, tails. Here, heads, tails, heads, tails. So when I look at this, this maps out everything that I can get. And so I'm going to use this tree diagram to write out the sample space, because it says use a tree diagram to list all the outcomes in the sample space that can happen when 3 coins are tossed. So what I could get first is heads, heads, heads. So that's the first thing in my sample space, heads, heads, heads. Then I could get heads, heads, tails. Then I could get heads, tails, heads. Then I could get heads, tails, tails. All right, that's the first 4. The second 4, assuming I get tails first, I could get tails, heads, heads. Keeping going down my tree diagram, I could get tails, heads, tails. Then I could get tails, tails, heads. And then finally tails, tails, tails. And this tree diagram, make sure that you don't leave anything out. You need to list all of the outcomes, and there's 8 of those there. And when you count, the ends on the tree diagrams is how many things should be in the sample space. So 1, 2, 3, 4, 5, 6, 7, 8. All right, now I can answer these questions because I can look at that sample space and see all of the possibilities. So first part, A, I want exactly 2 heads. So when I go over here, this has exactly 2 heads, this has exactly 2 heads, this has exactly 2 heads. So when I ask what's the probability that I could get exactly 2 heads, that occurs 3 times out of 8 times. Next one, I want at least 1 tail. At least means 1 or more tails. Well, that has at least 1, 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 so does this, so does this, so does this. At least 1 means 1 tail or more. That occurs 7 out of 8 outcomes, so its probability is 7/8. When I switch that on part C to be at most 1 tail, that's going to be 1 or less tails. So when I go through here now, at most 1 would be 1 or less. So this has 1 or less tails. This has 1 or less tails, 1 or less tails, 1 or less tails. All of those rest have more than 1 tail. So at most tails, at most 1 tail, that happens 4 out of 8 times, which reduces to half of the times. So make sure you practice that terminology exactly, at least, and at most. All right, going on to your next example, we're going to continue to do experiments. On this one, though, I'm not going to do a tree diagram because I think this one's easy to do without actually drawing out a tree diagram. Sometimes it's helpful, sometimes you don't necessarily need it. All right, so for this experiment, we have an experiment consists of spinning a spinner numbered 1 through 4, and then flipping a coin numbered with sides numbered 1 and 2. Find the following. So the first thing we're going to do is we're going to list out the sample space, everything that you could get if you spin the spinner and flip the coin together. And this one's pretty simple to see all of the outcomes. If you're teaching this in a class, of course it would be excellent to have a spinner and have this coin. Visuals are always helpful for our students. So the sample space, what I'm going to do, and I'm going to make myself a note, is I'm going to do the spinner outcome first and then the coin outcome. So sample space, remember you put in braces. So what I could get is I could get a 1 on the spinner and a 1 on the coin, or I could get a 1 on the spinner and a 2 on the coin. I could get a 2 on the spinner with a 1 on the coin, a 2 on the spinner with a 2 on the coin. I could get a 3 on the spinner with a 1 on the coin, or a 3 on the spinner with a 2 on the coin, or a 4 on the spinner with a 1 on a coin, 4 on the spinner with a 2 on the coin. And that's all the possibilities of things that I could get if I spin a spinner numbered 1 through 4 and flip a coin numbered 1 and 2. Okay, so that's S. Remember, we denote our sets with the capital letter. Part B wants for me to write an event. The event A consists of the outcomes where the number on the spinner is greater than the number on the coin. So I want to list the outcomes. That's going to make up this event, and these outcomes have to have the spinner number being greater than the coin number. So let me go through and see here. Here they're equal. The second one, the spinner's less. The first one I see is 2, 1. That's the first one where the spinner number is greater than the coin number. The next one would be 3, 1. And then I have 3, 2. And then 4, 1. And 4, 2. So that is event A. All of those outcomes have the spinner number being greater than the coin number. Part C wants a probability that the spinner number will be greater than the coin number. So the way you would write this is the probability that the spinner number is greater than the coin number. Well, when I look at that, that is the probability of event A. You could just write it. If you didn't want to write this, what you could write here is you could just write probability of A, event A. Go back to pen. So the probability of A is equal to, well, the number of outcomes that worked were 5 outcomes out of the original sample space that was 8. 5 outcomes met that criteria, so the probability of it happening is 5/8. Part D says event B. So we're going to write event B and all of the outcomes that meet this criteria. These are the outcomes where we have 2 consecutive numbers, but in any order. Remember, consecutive numbers are numbers that are in order, like 1, 2, 5, 6, 7, 8, 10, 11. But in any order means it could go backwards. So it could be 9, 8, 4, 3, etc. So when I look up here, consecutive outcomes, this would be consecutive, this would be consecutive, this would be consecutive. So there's actually 3 of those that meet this criteria. 1, 2 is consecutive, 2, 1 is consecutive, 3, 2 is consecutive. If I want to know the probability of that event happening, probability of V, well, 3 outcomes met that, so the probability of event B happening is 3 out of 8. 3 outcomes out of 8 total outcomes. Okay, next thing you have in your note is a couple of definitions. Those definitions are dependent and independent. So let me get back to that. Clear this off. All right, so independent events are events in which the outcome of one event has no influence on the outcome of a second event. So for example, if I spin a spinner and flip a coin, what I get on the spinner has no effect on what I get on the coin. Those are independent events. Dependent events are events that are not independent. So for example, if I think about the candy that we talked about. If I reach in and grab a piece of candy out of a bag and then I go back to reach in again, that bag has changed. My second draw is dependent on my first draw. Those would be dependent events. It says, note, events performed without replacement are dependent. Events performed with replacement are independent. So just because I'm drawing doesn't always mean it's dependent. Let's think about a deck of cards. If I reach in and draw a card from a deck and I put it back, I replace it, and I go back to draw again, those 2 draws are independent because the deck was taken back to its original state. Without replacement is dependent. With replacement is independent. So what we're going to do for the next few examples is we're just going to write independent or dependent. A says selecting a king from a standard deck, not replacing it, and then selecting a queen. Not replacing it means when you go to draw that second card, the deck is now different, so that would definitely make the second event dependent on the first event, so this would be dependent. B, tossing a coin and getting a head, and then rolling a die and obtaining a 3. Tossing a coin has no effect on what you're going to get when you roll a dice, so these two events would be independent. Okay, going to the last page on your notes, we have at the top, practicing the piano and becoming a concert pianist. Well, practicing definitely has an effect on how well you're going to do. So becoming a concert pianist is definitely dependent on the practicing. So these events would be dependent. Alrighty, on number 5, we have 3 boxes that contain letters. And this is, again, you could definitely bring this into your class, have these 3 boxes, and have your students a visual to look at. So it says the following boxes 1, 2, and 3 contain the letters. So box 1 has an M-A-T-H in it. Box 2 has an A, an N, and a D in it. And then box 3 has the letters in the word history. Question A says from box 1. So we are only using box 1. 3 letters are drawn one by one without replacement and recorded in order. What is the probability that the outcome is H-A-T or hat? Alright, so I'm only looking at box 1. I don't even have to consider box 2 and box 3. But the key here is without replacement. So the box is changing every time. I want the probability that the outcome is H-A-T. Well, what that's going to be is the probability of H times the probability of A times the probability of T. Well, the probability that I reach into box 1 and get an H, there is 1 H out of 4 letters. But that letter is not replaced. So once I draw one letter out, when I go in for the second letter and I want to get an A, there's only 3 letters left because I did not replace that first draw. So now the probability that I get an A, there is 1 A, but now there's only 3 letters. So now 2 letters are gone, so we can think the H, the A are gone. Now I want the T, and there's 1 T, but there's only 2 letters left in the box because we did not replace. Now we do the multiplication rule and we multiply. The probability that I get H-A-T is going to be 1 out of 24. On part B, we're going to box 1 again. 3 letters are drawn one by one, but the way that this changes is now we're doing this with replacement. And so same problem, but with replacement. So the probability that I get H-A-T is going to be the same thing, the probability of H times the probability of A times the probability of T. So probability of H times probability of A times probability of T. The probability that I get an H out of box 1 is 1/4. There's 1 H out of 4 letters. I put it back, I replace it, all 4 letters are there. So the probability that I get an A, there's 1 A out of 4 letters. The probability that I get a T, there's 1 T out of 4 letters. So in the previous problem, the total number of letters decreased every time because they weren't replaced. When they're replaced, all 4 letters are there. So when I multiply, the probability that I get hat, H-A-T, with replacement is 1 out of 64. Okay, going on to part C, 1 letter is drawn at random from box 1, then another from box 2, then another from box 3. With the results recorded in order. What is the probability that the outcome is hat? So now we're doing the same thing, hat, H-A-T, but it's not all out of box 1. 1 letter is box 1, 1 is box 2, 1 is box 3. So it's still going to be the product of those 3 answers, but now 1 out of each box. So let me erase this and move this up slightly so that I have room to write. Alright, so we can still see the boxes. Alright, so this time the probability that we get H-A-T is equal to, well, I want this H out of box 1. The probability of that happening is 1/4. That's the probability of H. Times, I want an A, but I want it out of box 2. So there is one A in box 2 out of 3 letters. The last one, I want a T out of box 3. Well, there's one T, but out of 7 letters. So this here is the probability of H times the probability of A times the probability of T. Same thing, but it's out of box 1, box 2, box 3, not all out of box 1. The probability of that happening would be 1 out of 84 once you do your multiplication. All right, and then last part here is part D. Part D says if a box is chosen at random and then a letter is drawn at random, what is the probability that you get an A? And you have to really think about this one, because on the previous 3 parts, I told you which box you were using. On part A and B, we were using only box 1. On part C, I told you you're going to take one letter out of box 1, then box 2, then box 3. This one, you're randomly choosing a box, and then you're randomly trying to get an A. So it's a little bit different of a problem. And so what I'm going to do is I'm going to do this in 3 steps. What is the probability that I get box 1, and then out of box 1 I get an A? Well, the probability that I get box 1 is 1/3 because there's 3 boxes. In box 1, the probability that I get an A is 1/4 because in box 1 there's one A out of 4 letters. So the probability that I get box 1 and then get an A in box 1 would be 1/12. Or I could think, what's the probability that I get box 2, and if I get box 2, I get an A when I draw a letter out of it. Well, the probability I get box 2 is 1/3, and then in box 2 there's one A out of 3 letters, so the probability that I get an A in box 2 is 1/9. The probability that I get an A in box 3 is assuming that I'm going to get box 3 and then get an A in box 3. Probability I get box 3 is 1/3. Out of box 3, there are no A's, so that would be 0 out of 7. So the probability that I get an A in box 3 would be equal to 0. So the question is, if a box is chosen at random and then a letter is drawn from the box, what is the probability that the outcome is A? So that's going to be these 3 separate probabilities. All right, moving on to number 6. It says, let me get to that one. Scoot this down just a bit. Hang on just a second. So in this one right here, it says, the following box contains 11 letters shown. The letters are drawn one by one without replacement, and the results are recorded in order. Find the probability of the outcome Mississippi. So we have this box. It has 11 letters in it. We're going to draw one by one without replacing, and I want the answer, the outcome, to be MISSISSIPPI. And so I'm going to say the probability that I get MISSISSIPPI. That's going to be equal to, so we have 11 letters drawn one by one. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different draws. Okay, the first thing that I want is I want an M, because I want an M, then an I, then an S, then an S, then an I. I want it to go Mississippi in that order. So what's the probability that I get this M right here first? Well, there's one M out of 11 letters. All right, that's not replaced, which is why I marked it out. Next, I want an I. When I look at this, there are 4 I's left, but there's only 10 letters left. So I'm going to mark that out. Then I want an S. When I count, there's still 4 S's, but now there's only 9 letters. And so I'm going to mark that out, just doing that to help myself. I want an S again, but now there's only 3 S's and there's only 8 letters. Then I need an I. There's only 3 I's left out of 7 letters. Then I want an S. There are 2 S's left out of 6 letters. I want another S. That's 1 S left out of 5 letters. Then I want an I. That's going to be 2 I's out of 4. Then I want a P. There's 2 P's out of 3. Then I want a P. There's 1 P out of 2 letters. And then I want an I. There's 1 I out of 1 letter. Now we could definitely go through and multiply all this, but I definitely think it would be helpful to go ahead and do a little bit of reducing here. And so we're just going to go through and reduce. Remember, when we reduce, we don't all have to reduce in the exact same way. So when I look at this here, I say in my eyes 2 times 3 is 6. Here 2 times 2 is 4. I can mark out this 3 and this 3. When I look at this, I can say 2 goes into 4 2 times. 2 times 4 is 8. And I look and see, and you know, you don't have to reduce in the exact same way I did. There's some variation in the way that you can do that. When I look, I don't see anything left in the numerator. So when I multiply my numerator, that would be 1. On the bottom, I need to multiply my 11 times 10 times my 9 times my 7 times my 5. When I do that, I get 34,650. So the probability that you get Mississippi in that order is 1 out of 34,650. Not very good chances of that happening. Okay, you will need to complete your homework in my math lab. If you need help, always feel free to contact me or email me. Please make sure you read the textbook. Remember, in my math lab, there are more videos that you can watch, PowerPoint that you can watch, examples that you can look at in your homework. One thing I want to show you, a really good activity that would also work for this day is on mathmashup.com. If you go to mathmashup.com, you can search by topic, and so they have a really good probability activity on here. Just go mathmashup.com, search probability, and it also involves candy. It's a really good little activity to list out the sample space. The reason I like mathmashup.com is because if you're a new teacher, sometimes you kind of need the activity shown to you, and their website has a video. Here's the video right here where it shows you how to do the activity with your students step by step, and then it comes with all the worksheets and activities and things that goes with it.